Sorry, I got a bit late. I should fire things up in a few minutes. Never can type. I think. Yes. Or maybe that. Yes, it's me. Save link, save. Okay, show all, downloads. I still have something to finish from the last week, so I'll fire that up. What is this? Okay. Let's get down to right, so let's begin. Sorry for the delay. So we were discussing data compression algorithms the last time around. Last week, towards the half of last week, we were talking about how do we deal with variable length prefix codes, recall? So we said our goal is to find an algorithm that mimics, or it does, you've used zip. So how do you losslessly compress text in this case? I'm just trying to make sure that my phones are off. Okay, so how do we losslessly compress text? And for that, we said our building blocks were variable length encodings for characters. And we talked about Huffman coding, and we said how easy it is to build, at least intuitively, what a Huffman tree is, coding tree is, and then any traversal from the root of the tree to the leaves, which is the real characters you observed in the text, will give you a path of binary bits, 0 and 1 bits, because it's a binary tree. Every time you're making a decision whether to go left or whether to go right, and then as you come to the tree, come to the leaf of the tree, you're guaranteed that path to be prefix free, because no path in a binary tree from root to a leaf will be a prefix of another path from a root to a leaf, because they have to branch out at some stage, so they'll be prefix free. Then we said the second ingredient we need beyond variable length character codes, variable length code for characters, is the variable length code for integers. And then we gave you an intuition at the very end, before we ran out of time, that you cannot just take the binary representation of an integer, and each integer would have its own minimal binary code. Minimal meaning that you don't have any zeros padded on the most significant side. So the most significant bit is always 1. So for instance, number 1 will have a minimal binary code of 1. Okay, number 0 would have a, well, number 0 is always an outlier. So 0 would basically have nothing but 0. But then if you have 1 or greater, you will have always a most significant bit of 1 followed by something. So 2 would be 1, 0, 3 would be 1, 1, 4 would be 1, 0, 0, 5 would be 1, 0, 1. So always the first bit is, the most significant bit is 1. And as the number increases, the bit increases. So it seems as if it's a variable length code, but it's not decodable. Because if I gave you a string of numbers, bits, of a collection of numbers, you wouldn't know where the endpoints of these things are. You could ambiguously chop those stream of bits and think about a communication that you would be having. So you're sending me something in a file. The file will contain a stream of bits, and I don't know where I should chop things up so that it is decoding exactly what you have told me, yeah? What you have put in the file, in the zip file. So you need something to deal with integers, and once we finish this discussion, I'll then go into the real crux of how do we actually use the variable length code for characters and variable length code for integers to drive a lossless compression algorithm on text. It's a very simple algorithm. It's an intellectually light lecture. Some of them are tricky, some of them are easier to follow, but this is surely easy to follow but real world. So everything, when you're zipping, you're going to do an algorithm that's similar to this, not quite too radical. Okay? So we already said what a minimal binary code of a number is. So that's a number 561. 561 can be represented with any number of zeros in the most significant part. But if you look at the minimal binary code, you chop away all the zeros at the most significant part. So you would have the order 2 to the power of 9 bit set to 1. So that's basically, if you ignore all these trailing zeros, you can have infinitely many zeros without changing what that number means, right? So you could have a binary, a minimal binary code for any integer. So we'll start with that. Okay, I must say that the code is for positive integers. So positive integers are integers that are 1, 2, 3, all the way to infinity. So you need a code that is valid for any integer which is countable. Okay, it could be any big number. Okay, any integer, it should still be a valid code. So you need a code. A code is a collection. Code is a collection of code words. So you need a code word for 1, 2, 3, so some code word all the way to infinity. Now, in some cases, so I'm not going to follow the slides slavishly. I'm just the slides for you to think about these things, but whatever I'm going to cover would be essentially everything I intended to cover on the slides. So 1 to infinity. So occasionally you would have coding for non-negative integers. 1 second. 1, 0, 1, 2, 3, 4, all the way to infinity. Yes, sir? I'm not sharing? Oh, okay, sorry, I didn't realize that. How does it work? Maybe does it work at all? I can see that there. Oh, that's better? Okay, thanks. So sorry, a code is a collection of code words for those who've not seen it on the stream. Was it streaming, Piyumi? This was streaming, right? Okay, a code is a collection of code words. 1 to infinity is what I want to build the code for, but occasionally irrespective of what we're going to learn, you'd also want to code for non-negative integers. Sometimes you also want to encode for negative infinity to positive infinity. But in mathematics, they are all called countable sets. The size of the set, 1 to infinity is same as 0 to infinity is same as minus infinity to infinity. If it doesn't make sense, no problem. Georg Cantor, a remarkable figure in mathematics, tried to convince lesser mortals like us that that's true, and people didn't believe him. People thought it's a pathology of his mind, but what we learn as set theory that arose around after pretty much became popular in 1920s, really. Georg Cantor was a remarkable figure who was snubbed for his contributions to set theory and how do you actually classify natures of infinity, for instance, is one of the small contributions he has done. But if the history apart, this set is same as this set. So the idea would be that if you have a code for a positive integer set, you could map that code to any countable set. You understand what I mean? So 1 could be used for 0 if you're counting from 0. Or you could do it from minus infinity to infinity in the way where you can say, well, I can say 1 maps to 0, 2 maps to 1, 3 maps to minus 1, 4 maps to 2, 5 maps to minus 2, and so on. You can actually do a mapping to negative infinity to positive infinity. But in this, so that was a general sort of an idea about how sets get mapped. But for you, we are now going to learn the code, integer codes for the positive, and potentially when you use it in Lempel-Ziv or compression algorithms, you would have to map whatever the code you get for 1 to 0, whatever code you get for 2 to 1. So we're going to use, in the real use, you would be using it in a non-negative sense. Okay? We will find the code for the positive, you'll be using it for the non-negative just by mapping. So it's a simple mapping, and that should be fine. Okay, is that agenda clear? Okay, if that is clear, the strategy is quite simple. For any integer n, you would have its minimal binary code. So the minimal binary code is called the code component. So there's some code component. For instance, if I had the previous slide, the code component for n equals 561 would contain 1 followed by that. So that's the code component of 561. You make sense? So then, this is not a prefix-free code. We already said that. Okay? You can't just code this and then, so what you have to add certain number of things to the prefix of it to make it a prefix-free code. Okay? That's the agenda. So what do you add? You have to encode some function. So let's call this length L1. So there are L1 bits. How many bits are there? 10, right? 0, 1 to 9. Can you see the red numbers there? So L1, for this example, L1 equals 10. So you would essentially coding as a prefix some function of L1. Okay? And that gives you L2. Okay? That gives you a certain width. I will talk about what that means in a bit. What is that function precisely? We'll make it more clear. What is this function precisely? So I'm going to code that. I have a prefix, but then it's still not prefix free. So I then have to take L2 and have some function of L2 to define L3, and I can keep doing this until the length is 1 bit. In a way, I want f of L1 to be, the function f to be monotonically decreasing, yeah? Or decreasing, so to speak. So let's basically use that as a yardstick to figure out what these precise functions are. So if you look at those bullet points, it says encode n, so that's the code component. And then all these things that we add up, we'll call them length components to distinguish between the real code. So length components are essentially encoding the lengths of the code in some decreasing way until you get one. Understand the idea? So, and the function it's saying is encode the length L1 minus 1 initially. So what is L1 is 10. So what is 10 minus 1? It's 9, isn't it? Okay? So I will change the color so that we can have some differentiation. So what is, so length minus 1, so L1 minus 1 is equal to L1 minus 1, that is 10 minus 1 is 9. So encode 9. What is 9 in binary, minimal binary code? Anyone? Put your hand up and say, what is 9 in binary? 1001. So it's early in the morning, so I'll believe what you said is right. I mean, I'm surely if I did that, I'll make some mistakes. So 1001. Okay, let's assume that we want to do this, okay? There's still some problem in this. We'll figure out, go through the works and then figure out what the problem is, okay? Okay, now what's the length? So 1001, how many bits was it? What's 4 bits? 1001. So now you do length minus 1, so that's going to be L2 minus 1 equals 4 minus 1 equals 3, yeah? So now you have 3 to encode next. So what's 3 in binary? 1, 1, okay? So how many bits is that? So now L2 equals 2. So length minus 1, so L3 minus 1 is 2 minus 1 is 1. What do we have next? So we have to encode 1 now. What's the binary of 1? Yeah, obviously, right? So I think you're all saying it's obvious, so I'll put it as 1, okay? You don't have to do anything more because you've now got to a point where you have this a function that has decreased down to 1 bit. Okay? Now we'll figure out, I mean, let's assume this code is prefix free. Okay? One of the things I want you to do in your self-study is why is this prefix free? Think about that in your self-study. Why is this prefix free? Now, problem is that is this decodable? Okay, is the code decodable? Okay, is the code decodable? Is it? It's actually not yet prefix free except for. Let's ignore the fact that it's prefix. Okay, I'll change my statement there. You'll have to still reason why the code we end up coming up with is prefix free later on. But let's pretend that that problem didn't exist. Can you decode this code if you had written it in this form? It'll be string of bits. Any string of bits is an integer, right? Any string, a string of 1 bit is an integer, 2 bits is an integer. So clearly you can't decode this code in the current form. Okay? Now, what did we have here? You had a code component, which was the main meat of the issue. This is what we need to encode. The whole purpose of trying to do this code is for decoding of this part. And you added some prefixes as a function of their respective lengths. So that's the code component. You have length component 1, length component 2, length component 3. In general, you could have any number of length components depending on the size of n. Okay? Can you see that? Can you imagine that? So there are really there are only two types of components. One's a length component and one's a code component, right? The length components could be many in the prefix, but there are only two types of them. You know that if it's a length so this is a length component of this is a length component of this is a length component of this, all these things are length components, and this is a code component. Okay, can you see that? Now, how can I tell that something is a length component and something is a code component if I had a code like this? I can't tell. So if I saw so let's say that your algorithm said any integer was encoded like this, and it is used the system of code component with the prefixes of length component in it. It ended in 1 bit. So when you start decoding it, you'll read the first bit because you have stopped at 1 bit. So when you're decoding it, you have to start at 1 bit. So decoding is the inverse of encoding, isn't it? You're encoding something into bits. Decoding is to decode the bits back into whatever you've encoded. So when you're decoding this bit, would you know a priori this is a length component or a code component? This could have been a code. So if at n equals 1, what would be this equivalent? For n equals 1, the code component would be 1. You've reached 1 bit stop. So the code for n equals 1 would be just that, right? So but could you tell, but this is a code component here, right? It's a code component. There's no length associated with it. Out here, this we know is the length component of the next one, it's the length component of the next one because of the way we wrote it, right? So if you are decoding it, you need to know what's the difference between a code component and a length component is, essentially. Is there any idea that you could suggest that during encoding, is there any idea you could suggest that allows me to differentiate what a code component is and what a length component is? Okay, it's not a trivial idea, just checking if somebody can come up with some method. Yes, sir?
Could you prepend the code component with a 0?
Can you?
Prepend the code, like add a 0 at the start of the code component.
Okay, let's assume that you had a 0 out here. So what's your idea?
With the code component without the 0, when we're actually placing it into the null or whatever, we add an additional 0.
Okay, so you kind of add an additional 0, but then when you come here, you would, let's say that this length component was 0, 1. How would you differentiate that this is a length component rather than a code component? 1, so that's encoding length 2. So that let's assume that length 2 was the 2 bits said 0, 1. You could have, could that be possible?
No, because if that's the case,
good, that'd be 1, right? So you stop right here. So if you had 0, 1, what's the value here? What's the value here? What you're encoding? 1. But what's the value it's encoding? It's encoding 1 minus the next one. So you potentially could have had 2 bits right here. Could you have 2, right? So you could have 2 bits right here, and those 2 bits could have been 1 1 0 1 1 0 and so on, right? So I think there are some limited possibilities. I think you are on to some scheme. I think I have to carefully think about whether you could work with the system, but I can see that there are some pathologies that could arise just by putting a 0 in between. But I think the message that I think you are trying to follow, the approach you're trying to follow is some way to differentiate between a code component and a length component, correct? Okay, so let's go back, remove this 0 that you suggested. Is there any more elegant way of dealing with the difference between code component and length component? By the way, do you notice that all significant bits, this has to be 1, we'll go back to the original statement. So 4 minus 1 is 3, so that's what that has to be 1, 1, right? So all the most significant bits are 1 necessarily, correct? All of them are 1 because that's a minimal binary code. Now what if I decide to do this trick? I know always my most significant bit is 1. That's determinism, right? I have full determinism that all my most significant bits are 1. All I have to do, so code component will have 1, length component will have 1 in the most significant bit. One way for me to distinguish between whether it's a code component and length component is read the most significant bit. And if I have intentionally during encoding, knowing it's 1, encoded it as 0, then that's a length component. If I have not encoded it as 0, then it's a code component. Is that a scheme that is viable? So let's see if that's true, then how do you decode this process? I'm not following exactly what's on the slide, but I'm covering everything that slide on that topic is covering, okay? So we can have a more dynamic discussion. So we're still looking at the example of n of 561. So the idea would be, so let's actually redo the process. So n equals 561 is that component, code component. It has 10 bits. 10 minus 1 is 9. 9 is 1, 0, 0, 1. I change that 1 to a 0. So rather what I've done is the most significant bit has been changed to 0 because it's the length of this one, of the code component. How many bits is this? 4. Still 4. If I've changed 1 to a 0, the length doesn't change. So 4 minus 1 is 3. I encode 3. 1, 1. Change that to a 0. So I'm just going to call it 0, 1. That's still 2 bits. 2 minus 1 is 1. 1 is 1 in binary. I change that to a 0. So I'm going to call that a 0. And then the length is 1 bit. Stop. So my code for 561, what's Elias code, it's a specific code of Elias, is 0, 0, 1, 0, 0, 0, 1, 1, 0, 0, 0, 1, 1, 0, 0, 0, 1. Okay? And that is a variable length code. And one of the things I want you to think about is why is this prefix free? Okay? Think about why this is prefix free. It's an exercise for you to think about. All right. So can we decode it? So when we are decoding it, so let's say that before you decoded it, you were right there. You have not seen any bit stream. So you're only seeing bits in a continuous order. In a file, that's what you're storing, right? Bits in a continuous order. But you're not storing them as a fixed length code. You're storing them as bits, right? So you're packing it into some integers and so on. But what you essentially are seeing is a stream of bits. At this point, you know that there is some integer that's been encoded using Elias code, but you don't know what that integer is. You want to decode it. How do I decode it? I'll say, okay, I know that if it's an Elias integer code, it would have ended with 1 bit, right? I would read the bit, the first bit in the stream that's to come, right? I don't know, there's a bunch of bits there. I'll read the first bit. Is it 0 or a 1 in this example? It's a 0, okay? So I know if it's a 0, is it a length component or a code component? Come on, let's be interactive. It's a length component, correct? If it's a length component, I can change that bit to 1, back to 1. What is the value of that bits? Here it's only 1 bit. What is the decimal value of that I've read if I change it to 1? 1. So the decimal value of this is 1. Okay? I have decoded 1. So length component, so decoded. So changing 0 to 1, I've decoded 1. Decode 1 in base 10. Okay? So which means, what is this encoding? It's encoding length minus 1 of the next component. So 1 plus 1 would be 2, right? Because it's this is length minus 1 of the next. So the next one would be whatever this is plus 1. So 1 plus 1 is 2. So which means, now read 2 bits next. So I've decoded 1. I know that this is going to be 1 minus the next component's length. Next component's length has to be 2. So read 2 bits. If I read 2 bits, is that a length component or a code component? What's the most significant bit of that region I've read? It's 0. If it's 0, I change that to 1, which means that I decode what is 1, 1 in base 10. If I decode 1, 1 in base 10, what is it? It's 3, isn't it? So decode 3, or rather decode 1 in base 10, decode 3 in base 10. Okay, so decode 3 in base 10. So, but that 3 is nothing but 1 more than the next component, the length of the next component. Next component has to be 3 plus 1, 4. So read 4 bits. Is that a length component or a code component? Well, it's again a length component. Change that to a 1. What would you decode here? You would decode 9. So decode 9 base 10, which means that the next component length would be 10 bits long. You go to 10 bits. Is that a length component or a code component? It's a code component, right? The most significant bit is 1. So always checking the most significant bit. The moment you get the most significant bit as 1 in any read that you are doing in this algorithm is what's it doing? Read a certain number of bits, decode. Is that a code component or length component? If it's a code component, stop, decode and stop. If it's a length component, decode it, add 1 and read the next. So you're doing a repeated algorithm. So once you get here, it's a code component, 10 bits, that if you decode, you would decode 561, which is the original n that you started with. You see what I'm trying to say here? So essentially, the algorithm, all on the slide, you have this thing about what I said, just adding length components and code components without changing, without having a way of distinguishing between what's a length component and a code component is problematic. So what you then do is do this method of changing the lead 1 to a minimal, the leading 1 bit to 0 to distinguish between length components and code components in some form. And then, yeah, so, and if you did this process, I mean, same example, I think I've just did this example where you had this code. You can see that 001, 0001 followed is the code you would get. Okay, so whatever I've told on the board as a process is on the slide. Is that roughly clear what we're doing here? And then decoding is also easy. Before we do decoding, can you see, look at the table. So all you have to do is the first column and the last column. So first column and the last column. For integer 1, code component is 1. Do you have any more length components? You don't, right? You just have 1. So when you decode 1, the first component would be 1 bit. Is it a length component or a code component? It's a code component, that's it, the decoded 1. 2, the code component is 1, 0, the length is 2, 2 minus 1 is 1, so you're going to encode 1 in binary, but changing the most significant bit from 1 to a 0, so it's 0, 1, 0. Can you see that? 3 would be 1, 1, again, length 2, 2 would be, 2 minus 1 is 1, so you're encoding the length component as 0. 4 would be 1, 0, 0. It has 3 bits. 3 would be 1, 1, 1, 1. 1, 1 would be, sorry, 3 minus 1 is 2. 2 would be 1, 1, 0. So 1, 0, the most significant bit is changed to a 0, so it's become 0, 0. That's 2 bits long, 2 minus 1 is 1, that's going to be 1, 1 has to change to a 0, and so on, okay? I'll just do one last for 16, so that you usually have these big jumps in the code at certain certain values for certain integers. For 16, can you see 16 is 1, 0, 0, 0, 0. That's 5 bits long. 5 minus 1 is 4. 4 would be 1, 0, 0, but 1 has been changed to a 0. Okay, that's 3 bits long. 3 minus 1 is 2. That's going to be 1, 0. 1 has been changed to a 0, so 0, 0, then and so on. Now, this code is prefix free. This works for any integer. Imagine what a clever code this is. It will work for any integers from 1 to infinity. It's not a finite set. It's an infinite set. Now, what you have is the component sort of lengths given here. So to speak, the component values. So that's 1, that's going to be 2, that's going to be 4. So if you had 1, 1, 1 in the length components, that would be the values that you would see. 1, 2, 4. So 1 out here would be 1, 1, 0 would be 2, 1, 0, 0 would be 4, 1, 0, 0, 0, 0 would be 16. So you don't have to worry about this component. It's just for you to guide what you have included to the code component, but really the first column and the last column is all you care about, and then you can decode. Decoding also we have done. You can start with some, so there's some process in which whatever I've told you about how do you start with one bit, decode, you start with the first bit. Is it a code component or a length component? The answer is it's a code component, decode and stop. If it's a length component, decode, add 1 to it and read those many. Next. Is it a code component or length component? Code component, stop. Otherwise, length component, decode, add 1 to it until you sort of get the code component and stop. So you would have to stop this process at some stage if you encode this correctly, and I've already worked out this during the lecture. All right, so what have we achieved here? We achieved 2 simple atomic operations, 2 simple encoding schemes, one for a character, one for an integer, right? Now, how do we then take this building blocks to drive a text compression algorithm, okay? So Lempel-Ziv, two Israeli computer scientists in 1970 came up with beautiful algorithms that sort of are embedded in all your compression schemes that you use. Okay? In any form, if you're using gzip on Linux, it is using a variant of Lempel-Ziv. Okay? There are Lempel-Ziv, Ziv-Lempel, Lempel-Ziv Welsh. So, what we are starting here is an algorithm that is, you could just use this algorithm and get as good of compression that you can, write a very real-world compression algorithm, which is the aim of the topic, and that's what we're going to do now. See how we're going to use these 2 encodings and drive it. So what we're going to do is Lempel-Ziv 77. So it's an algorithm that was proposed in 1977, and then there are many variants of that algorithm after it was proposed. One variant we'll also see is Lempel-Ziv, Strorer and Zymansky. I think the names of 4 other people. So names of 4 authors, or Strorer and Zymansky building on Lempel-Ziv. They call it LZSS, LZSS. That feedback, I don't understand why I keep getting that feedback. Okay, so what's this algorithm? We'll get into it before we see what this algorithm does. So it involves examining input text through a sliding window. Okay, we'll see what that means. It contains 2 consecutive paths. Okay, you can think of, I like to think of it in the following way. You might want to find a way to describe the algorithm to yourself in a way that you understand. I will just clean up the board. So that's a string. Always a line for us is an abstraction for a string, text. In some state of your algorithm, you are processing the string in some intermediate stage. Think about it in some intermediate stage, then we'll start from the beginning with an example. Intermediate stage, you're thinking about, you're somewhere in that string. So it says you have a window that is sliding. A window, let me actually draw that window. Doesn't have to be symmetric. So your point is there. You could have some past with respect to that, some context with respect to that arrow, some past and some future. The window is this. Okay? And that is sliding. Okay? You're sliding that window in some form. Now, what is that? We have a part which is called the search window, the 2 parts. So everything before this arrow is the dictionary, okay, or the search window, or the context. So wherever that thing is. So the idea is that everything before, the past has been done, processed. You've already done, encoded stuff. You've compressed the stuff. You're compressing future, but the only visibility of the future is dictated by this parameter W. So we'll see what that means with a concrete example, but here's intuition. So search window, and then you have a look ahead buffer. So I'm just going to change the color. So all this is the look ahead buffer. Okay? So you have a search window and a look ahead buffer. To encode any character or a substring, so your point of encoding is this black arrow there. So it's that character or beyond. If it's just one character, it would just be a character. If it's a substring, it will be a substring starting at that point. So your point of encoding any character or a substring is in the look ahead buffer. To do that, you have to find what is the largest substring starting at a point that matches, so let's call that alpha. Sounds very familiar with this kind of finding largest something. So let's say you have alphas, you could have potentially alphas that way, and there's some x, there's some y, some z, doesn't matter what comes out after it. So it's the largest substring starting at this point that matches something, but not anywhere in the text, it's only in that dictionary. And I'll tell you why it's not anywhere in a bit, but you're just giving you the drill of the algorithm, just to give you an intuition of the algorithm. So if you're trying to encode the largest match substring in the dictionary, in the search window, so you're trying to only search it in that dictionary or the context that you have in the past, everything beyond that window is gone. It's evaporated. So you don't have a memory of it. And you kind of have, you don't have a vision of what comes beyond this either. So these ends are your light cone. It's the limits of where you can see in the past and the future. Okay? So there are 3 pieces of information that you have to encode. Okay? If I found some alpha, some largest substring that matches in the dictionary, how far away from this point is it? What's the offset? So let's say it starts here. What is the offset of this black one with respect to the green? Or if it starts here, in fact there are 2 copies of it. I intentionally put 2 copies so that I can come back and say which one would you want to say. That's P1, P2. So P2, and that's basically I. I is at an offset with P1. I is also an offset at P2. You are encoding one of these distances, the gaps between them. Offset, length. Length would be the length of alpha. And then you also are encoding the next character in the look-ahead buffer after the matched one. So essentially, you are encoding. So you have to say how far is alpha in the previous context. So if let's say this was 20 and this was 10, it's at an offset of 10. Okay? And then if it's of length 5, if alpha is of length 5, so you're sending length 5, and then you have to send what is the next character associated with it. So your three things you're encoding. 3 things are the offset, the length, and the character. Do you know an integer code for integer? So do you have a variable length code for integers? For this one, length can be of what size? Offset can be 0 or more, because you can't, if you don't find anything, there's nothing for you to find. So 0. Length can be, again, if you don't find anything, length can be 0 or more. And then you have a character. Do you have a variable length code for a character? So all of these are variable length codes, really. So although there are pieces of information, you're encoding it in a prefix-free code. One with alias, this thing. Now, only thing is that alias that we discussed was with respect to a positive integers, 1, 2, 3, 4. But this can be 0, right? So you have to have a mapping of code for 1 to map for 0, code for 2 to map to 1, code for 3 to map to 2, and so on, right? So whenever you are encoding it, 0 implies the code for 1. You understand what I mean? Okay, so that's clear. So let's take an example, and then we can move on with it. So you're encoding offset, length, and char as a variable length scheme. So if you look at what you're putting into your file, and you look at a zip file, have you ever opened a zip file? You take a text file, zip it. Have you opened it in Notepad? Do this experiment. Do you see gibberish? Okay? Do you see some garbled text? So really what's happening there is variable length code, which your Notepad is interpreting as a fixed length code. Because Notepad is reading 8 bytes at a time and trying to display a character to associate with it. Or some UTF-8 encoding, or UTF whatever encoding that you have set your locale to be, whatever you have configured your system to be. You understand what I mean? So all these things come in variable length code. So you cannot possibly look into the file, read a file with your editor and say, I understand it. And that's the reason why you will see rubbish in your code, or something that you can't make sense, because essentially the algorithm has done variable length codes and you're interpreting it as a fixed length code. Okay? So it's not a legitimate decoding. So your Notepad is decoding it incorrectly. Although when you unzip things, or you whatever decompress it, whatever you call it in Windows, or gunzip or B unzip and so on, so many other versions, when you unzip something, then you basically get the algorithm to decode it to its parameters. So if I have a decoding algorithm for lempel-ziv, it's saying I expect 3 pieces of information, one encoded as an integer, second encoded as an integer, third encoded as an Huffman code. And I keep doing this in a certain number of times so that I can get all the pieces of information. Okay, let's see an example. Okay, that's our text, A, C, C. Maybe it's worth writing it explicitly. So A, C, B, C, B, A, C, okay? So some string like that. Can't keep a line when I'm looking up. So what's my window size? So first thing is the parameter to your program should be your window size. Now, have you ever stated any window size in zip? You just said zip and it did that for you, isn't it? Now, in fact, if you were doing it on a command line, if you're using a gzip, it will have -1, -2, -3 options, okay? These are levels of compression. So it will by default, it's set to a certain window size internally. You didn't have to make the choice. But if you are writing a compression algorithm, you will have to define a parameter of what that window size is going to be. So the window size I've chosen here is 10. Okay, it's 10 because it has a search window of 6 and a look ahead window of 4. Okay, you can actually define it as two parameters, past and current plus future, right? So if you say that my window size, instead of saying my parameter is 10, my parameter is 6 and 4, where 6 is what I have in the past and 4 is what I have in the future. Okay, that's what it is. Now, in general, in any iteration, when you see this orange line, I'm just showing you some middle iteration, you can see that you can see 6 characters behind, 1, 2, 3, 4, 5, 6. So that's basically your dictionary size. And you can see in some algorithm, in some iteration, you can see 4 characters to the right of that yellow line, that orange line. So the green line is where the search window ends at the left, and the red is where the look ahead window ends on the right. Okay? So you're going back that way, going forward that way. Okay? The search is basically at any iteration, and this orange line is like that arrow that we pointed. Instead of putting the arrow there, I'm putting that line there. That orange line is basically separating the past, the present, and the future. Yeah? See, understand what I meant there? Okay, so we will look at this window size with a past of 6 and current plus future of 4. Okay, look ahead is 4, implies that wherever your pointer is, the pointer would be the first character of the look ahead every time. Every time, that's where you're going to be. So when you start the algorithm, is it fair to start the algorithm there? When you start the algorithm, you have to start at the left end, right? You're compressing. The goal, what's the goal? I want to compress this text as efficiently as possible. When we start there, what's my past? Nothing. Have I seen anything before? Nothing. Yeah? My past is nothing. So what do you have to encode? The longest substring starting at that point that matches something in the past. But you have no past, which means that the offset is 0, the length is 0, and what comes after that match is the character that you have to encode. Okay? So you have to, so it's calling, you're saying, I have no past, so there's nothing to copy of length, and the character is A. That's the character I've copied. Yeah? Can you encode 0 in variable length code? What's the variable length code for 0? Anybody? Remember what I said about mapping? Positive to non-negative? So 0 would be, you're going to use a code word for 1, isn't it? What's the code word? So 0 is mapped to 1, 1 is mapped to 2, 2 is mapped to 3. So code word for 0 is 1. Okay, the reason is it's mapped to 1, code word for 1 is 1. Okay, so although I'm going to call them as integers, you have to think about them in variable length codes. Okay, don't forget this. Okay, so 0, 0, so that's going to be, the bits would be 1, 1, and can you build an Huffman code for this string before you started this algorithm? So can you see that there's some number of A's, some number of B's, some number of C's, and so on, right? And they're not equal, are they? I mean, at least if they are equal, they are just by chance. But in general, if you're writing text, Q will not appear same number of times as A or I, right? So you can essentially, before you started this algorithm, you could have a Huffman code for the characters. So which means that when you're encoding A, you're encoding using the prefix-free code for A. If you see all A's, it will be a fantastic, instead of having 8 bits for an A, you would basically have 1 bit for an A. If you have all A's in your string, there's only 1 bit you need to encode any prefix-free code. Yeah? So 00A. So you understood how this tuple came? Offset, length, and the character you're after that copy. So there's nothing you copied, so character after the copy is A. Would you agree that now I have my pointer there, I've finished encoding A? Repeat the process. What is the largest copy that I can get in the past? My past is only of 1. Although my past window is 6, there are only 1 that has arrived in the past right now. Okay? So what's the future? The future that I can see is only up to this point. Okay? So what's the largest I can copy in the past that matches this string? So I can go back 1 letter. A matches with an A. Does C match with A? Although it's crossing the boundary, if I have copied something, I'm allowed to cross the boundary. Okay? So A matches with an A. Okay? We'll see why we are allowed to cross the boundary when we are decoding. So A matches with an A. C does not match with an A. Okay? Okay? This process should not cross this line. Copying should not cross this line because nothing else is known here. Okay? I'll tell you why you need those window sizes in a bit. So the next tuple would be go back by 1 position, copy 1 letter, and the character after the copy is C, isn't it? So you are going to encode integer 1, and C in the Huffman code. Integer 1 maps to 2, so the code for 2 is what you would be encoding for that one, right? Now, I have, how many letters have I, in between those two tuples, how many have I finished? I've basically finished until this part, isn't it? Because A has been copied, then copy A, and then C, that's what the C is. My point is here. Now I have 3 letters here. What's the maximum I can copy? Okay? So what is the maximum that I can copy? So my window 1, 2, 3, 4. Okay? What's the maximum string I can copy in the past? So can you see the numbers? 3, 4, and B. So I can copy this. I can copy this. I can copy this. I can copy this. And I have nothing. I can't see anything. Technically, I can potentially write the algorithm to see only one after the end, okay? One after the end. So I can copy this, okay? A, C, A, and then I've reached the end. Irrespective of whether I could continue, I have to stop at that point because the look ahead stops there. I'll tell you why we need that in a bit. So that would be go back 1, 2, 3, offset is 3, copy 4, and the next character is B. Does that make sense? What I'm doing there? And 3 would be an integer code, 4 would be integer code, B would be an Huffman code. And the process sort of repeats like that. So now I have everything until this covered. Okay? All that information has been covered so far. Can you see that if you have a long copy, you have in 3 numbers or 3 pieces of information, you have stated quite a bit of information. That's where the compression comes. Can you see that? Can you see how the compression comes? So once you're here, so you're right now there. So what is the largest copy? So it says that go back 1, 2, 3, and copy 3, C matches with C, A matches with A, B matches with B, but this does not match with this, so it has to be 3, 3. What's the next character after that? It has to be A, isn't it? So it's CAB matches CAB, next character is A, so, and so on. I don't have to keep doing the whole example. You understand what I'm trying to do there? Okay. Now, why did we choose to limit our past and the look-ahead buffer? Anybody? Does anybody have a sense of why we chose? Why weren't we looking all the way to the start and all the way into the end? The offset would be big, okay? But what's the problem? We have a code word that allows you to code any integer, so offset would be some big integer. In fact, so what are we doing at each step? We are trying to find something, right? Okay, so you need a data structure that is able to pre-process. If you did not have these windows, you would have to have a data structure that pre-processes the string that you are compressing, and then it's able to find out the largest occurrence, okay? And we also have this question, what happens if you have two occurrences at different positions? You can actually have, remember the original example had alpha in two different positions? Which one would you encode, P1 or P2? I mean, offset to P1 or offset to P2 from I. We'll come to that, but if you just focus on why we had these things. So what would happen is that your data structures to search will grow in size proportional to your text, and often you're compressing gigabytes of information, okay? Then people said, well, it's unwieldy to process so it's very common to compress gigabytes of information, right? So megabytes would be millions, gigabytes, okay, very common. Like if you're doing anything useful in real world, gigabytes just get generated like that, okay? So you don't want to have a pre-processed data structures that are for compression that's so memory intensive, because they have to be in your memory for you to be able to drive this algorithm. So what happens is that if you have this space in memory, you will get the most compression you could gain for an algorithm. So if you can see the past to the start and future to the end, you would actually end up getting the most compression possible under the scheme. But the problem is it has a memory pressure, okay? If you have gigabytes, sometimes it's easy to have hundreds of gigabytes compression, right? Very, very common to compress it. Very, very common in many real world applications to compress it quite regularly, right? So then what's the compromise? The compromise is that let me have my window size define how much memory I can store while running this algorithm. So essentially my window size is dictating how much main memory, maximum main memory I can maintain while compressing this text. So, but what's the trade-off with that? The trade-off is you might have got a larger copy of a larger length if you did not have the window, but now you have to have the copies dictated by the parameter W. Now in reality, for most text, that's not an issue at all, because most text, the copies won't be gigabytes long, billion characters long, very rarely, unless you're doing some text in a special case of genomes where you have 3.2 billion letters for human beings, and then you would basically say the second human being is much like the first human being that I've seen, 99.99% similarity. So the copies are going to be very big. The first time you have one copy of genome, the second copy is like, oh, it's just like that. The third one is just like that. So the copies would be very, very big. But really, what you're compressing is code or text, unless you have copied code from somebody, the copy would not be, oh, maybe I should use compression algorithm to see what's the similarity between two codes is. Anyway, so just joking. So if you're just copying stuff, it could be of different lengths. Can you see that the lengths are not going to be too big? So in which case I can have a practical limit of how big my window would be. And often you would have, if you say my window is 10 megabytes, 10 megabytes doesn't seem like something that you would, in these days, you would even think twice to use as a window size. 10 megabytes would be what? 10 million characters long. Okay, so that's quite a large space. And for most practical purposes, that will be a good choice for you. And when you run an algorithm, the default would be something like that. Unless you're doing 7-zip, which has a much more larger version of 7-zip uses Lempel Ziv, other variants of things. So essentially, if you want to have a very large memory footprint, then you get most compression. If you have very small memory footprint, you get lesser compression. So what you see as flags -1, -2, -3, if you're running, let's say gzip -1, so levels of compression. -1 would be very little memory footprint. -9 is the highest level, the maximum footprint. And I think the default would be something like 6. It will set as a trade-off between how much compression you would get, how much. Yeah, does that make sense? Now, by the way, when you are decoding it, if you know how many tuples there are, so if you know how many tuples there are, so let's say that you went ahead and wrote this algorithm to a file in a variable length way. So if I encoded number of tuples, some amount of information, so some information, let's call this header. So number of tuples, okay, and then number of unique characters. How many unique characters do you see? 3 here, right? So n unique characters and the Huffman codes. So for each unique character, you would be a Huffman code. You would have to construct a function of your string, right? It's a property of your string. If you have a header with this information, then you read the header. How many tuples does it have? What are the unique characters in it? And what are the Huffman code? In which case, 1, 2, 3, 4, you could decode this using decoding integers and Huffman codes. You know what Huffman code is? You know how to decode an integer? You know what the information of the Huffman codes are? You could decode this whole thing. So that's what, when you unzip, that's what happens. So you'll have the header and the information that you've encoded. Does that make sense? Roughly? Okay, so I just wanted to say one more thing, a couple of things to talk about. If you had, I'll erase this. So if we had some alpha that, so this was a window, and alpha appeared here, alpha appeared here, that's P1, that's P2, and this is the current position you're encoding. So this is the past, the dictionary. So what is the off, would you consider giving an offset to P1 or offset to P2? Which one would you use? Why would it be P2? Good answer. And if it's smaller, the integer code would be smaller. Correct. That's a very lucid answer. Thank you. So you always, if you have multiple options, you would always choose the one closest to I because the offset would be small. Variable length code for small would be smaller. What's the goal of compression? Fewer number of bits. Smaller is good, right? You want to do something that's smaller. So that's one aspect of it. The other aspect of it is, I'll just do one example. So let's say that when you're decoding, so let's say you've decoded 0. So first, when you're decoding this, whatever the variable length code, you decode, you said, okay, the offset is 0, the length is 0, the next character with Huffman code is A. So you write A, okay, you decode A, and then you come to the next tuple, said, okay, so you got A, you've decoded A, you're now decoding the next thing. You will see 1, C, so go back 1, copy 1, write C, okay? Then you would come to the next part. Then next part is what? 3, 4b, that's a tuple. Whenever you're decoding these things, you get 3, 4b in your decoding algorithm. So 1, 2, 3, copy 4, and decode b. Can you see that? And then so on. So I'm just going to continue. So 3, 3a. So previous 1, 2, 3, copy 3, C, A, B. Next character is A. And next would be 1 and 2. So go back 1, copy 2, A. So first copy, second copy. Okay, can you see? The reason I'm allowed to copy beyond the yellow, the orange line, beyond the orange line is because if I've copied it, I can also decode it in that successive order. Okay, so technically, when I say go back 1, I only have one piece of information, not two pieces of information. It says go back 1, copy 2, but I only have one piece of information in the past. But once I decode the first one, I have now two pieces of information. So next would be that. And next would be C. So that would essentially allow me to do the whole thing. Is that clear? Okay. A very simple variant to end this discussion problem is that often you would have this offset size. So offset length char is the encoding for Lempel-Ziv 77. LZ77 uses these tuples. Offset is fairly big, but the length is fairly small. So you could go back, if you have 10 million characters in real world, you can say go back 3 million characters ago, copy 2 letters. That's not going to be useful, isn't it? I mean, it's a waste of space for encoding such a big one. So what Strorer and Zymanski did as a variation for Lempel-Ziv is said, well, actually, we will use these the way of copying of offset length. So offset length scheme we'll use if it exceeds a threshold of length. But if it doesn't exceed a threshold of length, I will have to change my coding scheme to simple character-based encoding, just one character encoding, Huffman code. And so what they did was, now they have the same problem of when do I switch? When I'm decoding, have you coded it with one set of tuples or the other set of tuples? So it's very easy to tell between the two by adding an extra bit, saying if it is 0 bit, if I've flagged it with a 0, it means that it has an offset length encoding. If I flagged it with a 1, it means that it is a character encoding. Does that make sense? Just a simple example. And they used this cutoff of 3. And I actually asked Strorer, he runs a data compression conference. So I asked him, he runs so he's from University of Utah. I had a chance of meeting one of the authors, and I asked him why 3, and the best answer he gave me is that at the time when they were analyzing text, that seemed to satisfy it's an empirically chosen threshold. Okay, there's no magic behind this, beyond the fact that it is just empirical given the codes of encoding that they were doing. So there's saying that if the length of the copy is greater than or equal to 3, so if it's 3 letters are wrong, it pays to use by and large an offset length encoding, otherwise just encode 1 letter. Okay, and let's see an example here, the same example, but I'll only do a few. So same example, same window sizes. When you start here, there's no copy. So previously you would have said 00A, right? But now you're saying, well, it's a character encoding, so flag 1 bit, put an A, okay? So there only one implies the character encoding. Now you have one character, that's where you are. What's the copy? It was like last time you have a copy of 1 at offset 1, and the next character was an A. Previously you would have done 1, 1A. But now the copy is of only size 1, it is less than 3. If it's less than 3, okay, just do the character encoding. Okay? So character encoding is 1A. So now you have those two encoded. Your pointer is now here. What is the largest copy in the past? Starting from this point, well, none. I can't find any C. So previously, whatever you have done, so let's assume that you were starting Lempel-Ziv from this point, you would have done 0, 0, C. But then now, because there's no copy here, so you just say 1 C. So it basically gives you those AAC. All of these have been encoded with a 1-bit flag, but it gets interesting here. Out here, I have, what's the copy size? At offset 3, I can copy 4. So I can copy A with A, the second A with the second A, C with a C, and then I can copy A with an A. And essentially, I've reached the end of the buffer. So I don't have anything to look forward to. Previously, we were allowed to look to the next character. Out here, there's no next character. So you can say, well, the copy is 4. 4 is greater than the threshold. So remember, the threshold was greater than or equal to 3. If the length is greater than or equal to 3, I put a 0, 3, 4, which means that all these characters have been copied. I can restart the algorithm from this point. This point, is there a B anywhere? What's the longest substring that I can find? Well, there's nothing, so it has to be 1B and so on. Okay, so it's the same algorithm, and the decoding is much the same. Okay, so just go through this example, and I think that sort of ends the discussion. Okay, I want you to think about what optimizations you would use and what were the variable length codes. How could you actually use that during your self-study? I will be releasing the assignment 2 this week, so keep in, sorry guys, you'll have sufficient time. You have a break as well. So, and then as usual, I'll be holding 3 different consultations regularly. Okay, maybe initially 2, but yeah, assignments don't. I feel that this will be a much, it'll be an assignment you will enjoy. Okay, it's also the biggest assignment, 20 marks. Okay, so you'll have more time. At least I think I'll try and give you 4 weeks, including the break. So, but if you are trying to do the assignments in the last week, that's not the strategy. I've already told you. So, all right. So we will. I'm still running a bit slower than what we have, but I will catch up at some point if we. So we have some time to go through at least the initial aspects of semi-numerical. It will spill over after the break. Doesn't matter. I will cover everything that needs to be covered, and at some point we'll catch up. Okay. Sorry for that staggering. It really started with Yukonen. Yukonen took longer than 2 hours. That's why we have that stagger. So we're going to talk about semi-numerical algorithms. So what is semi-numerical? That's the name that Knut uses for his volume 2 in his book. So they are number theoretic. Numerical implies floating point usually, floating numerical algorithms, so floating point algorithms. So like if you're doing any linear algebra, any sort of continuous mathematics, those kind of algorithms. Semi-numerical often means integer-based algorithms. Okay, and so and there's a beautiful treatment across these references. I mean, at least Knut's volume 2 is a classic for semi-numerical. So for all the good students who want to do over and beyond what is there in the, when I say good, everyone's good, but all the students who are keen to study over and beyond their course material, I'd strongly recommend volume 2. Okay, at least I've enjoyed over the years. You never read it in one go, but you keep reading it. There's always something new you would learn in Knut's books. Okay, so we're going to talk about number theoretic algorithms. They're prominent in cryptographic schemes. These schemes rely on large prime numbers, and feasibility of your cryptographic systems, at least in the classical computing era. If quantum computing comes, God knows what's going to happen to our cryptographic schemes. The feasibility depends on generating large primes, and the security depends on the fact that we cannot factorize prime numbers easily. Okay. whenever we talk about complexities of algorithms, the complexity of algorithm was always the size of the input, right? Of size of the input, we said it's an n squared algorithm, n log n, and so on. Whatever the size of the input told us what the characterization, everything was a function of the size of the input. But when you talk about complexities of number theoretic algorithms, semi-numerical algorithms, you don't have to, you have integers. So what does it mean, the one integer? Let's say, what's the complexity of testing the primality of a number n? Okay, well, there's only one. How can you define the complexity in terms of one input, right? If you're testing whether a number is prime or not, it's often in number theoretic algorithms you try and define complexities in terms of the length it takes to represent that number. It's the length of that number. Okay, so if you have a number n, what is the length? In general, I mean, if binary code of n would be how long? Roughly log n, isn't it? If you have a number 16, 1, 0, 0, 0, 0, right? So that's log of 16, okay, plus 1. I mean, floor of log 16 plus 1 is what you would, the size is. The exact size is the floor of log n plus 1, okay? So 15 would be 1, 1, 1, 1, right? So 4 bits. Log 15 to the base 2 is 4 bits, right? Essentially, is in the order of that. So, you're defining the computational complexity in terms of the number of bits required to represent that number. So, if a number n takes d bits to represent, you have floor of log n plus 1 bits to represent that number. So, the complexity is a function of d, not n, okay, or not the input size or something like that. So if a linear time algorithm is one that runs in O of number of bits it takes to represent a number, a quadratic time is O d squared, etc. A logarithmic algorithm would be O of log d. Does it make sense? So it's just the size that defines. Okay. What am I going to do? The plan for this lecture, at least what is remaining plus after the break, is I'm going to, just as in the previous lecture, compression was a goal and we had some building blocks. So I'm going to have some building blocks. The goal is primality testing. Okay? And in fact, it is introducing an extremely real world algorithm, Miller-Robbins primality testing. And it also is introducing a new problem solving technique which you likely never solved before. Okay? You would have solved problems which were smaller that became incrementally bigger, okay, like the minimum spanning tree. You would have done divide and conquer, quick sort, that kind of algorithm. You've done dynamic programming in some part. So they're all problem solving techniques. But here's a problem solving technique which is based on random numbers. And it's a randomized algorithm. So what we are going to learn is an instance of a randomized algorithm. It's a powerful class of problem solving, and we're going to do it for Miller-Robbins is an example of a randomized algorithm. Okay. By the way, this is a randomized algorithm that's used in everywhere. All cryptographic systems use it. Okay. So what you're learning again as one of the missions of this unit is that every week you're learning something that is cool and real world. Okay. So it's not just theoretical. If you're doing computer science, these are what happens as bread and butter in some places, yeah, in various places. So the building blocks I'll start with is how do you multiply two integers? And you might ask me, Arun, if you take two numbers, A and B, do A times B, output the answer, right? So I'm not interested in how you write the code, but when you say A times B, what is that times doing internally? Okay. Have you ever wondered this? So what's the cost of doing a multiplication of an integer? Anybody? So it shows something on the screen, but on a computer, when you multiply two integers, what does it mean? It's basically multiplying two integers represented in some form your hardware has a hardware implementation of an integer multiplication. Okay, Wallace multiplier. In fact, that algorithm arose from somebody who founded the computer science department. It's there in every single electronic device that you see. The Wallace multiplier is an algorithm that is hard coded on your chip when you're multiplying two integers. But they can only multiply two fixed width integers. If the integers fit in those number of 64-bit registers, whatever general purpose registers that you have, you could basically then let the hardware drive the logic of multiplication in constant time. You can say that it's constant because the integers are based on a fixed width representation. But if I asked you to multiply arbitrary length, and your Python uses a big int class, isn't it? If you can type up a long integer a and a long integer b, it will have to figure out how to multiply it in a software. An algorithm has to do that. It might end up using the hardware implementation as a base case, but at some point it will have to say, how do I multiply two integers? And remarkably, this problem has a fairly recent advance, while human beings were trying to multiply numbers for more than 2 or 3 millennia, right? Multiplication seems like very important for us. Okay? And you can think about the multiplication you learnt in school, long multiplication, 1, 2, 3 times 4, 5, 6. Essentially what you're doing is 4, 5, 6. So 4, 5 and 6, I'll just write it out on the board. So 4, 5, 6, what base is that written in? Well, it could be in any base, but what are you interpreting that number as? In what base? Base 10. That's a base 10 number, isn't it? So really, you can think of this algorithm in any base. So base is not important, right? Converting between base is just a multiplier by a simple log factor. So you can convert base 10 to base 2 by taking the length would be whatever the base 10 times log 10 to the base 2. That's about 3.3 bits, and so you could convert the same thing into the size in the bits. So I'm writing it in base 10. It's easier to see it in base 10, right? So if in base 10, whatever I'm telling you right now is true for any base. So this number is really, you're reading this number as 400 in place value system plus 50 plus 6, right? That's what you're doing, 456. So why did I have, so here there are no zeros, there's 1 0, there's 2 zeros. If I had an extra, if I had a 1 there, that would be 1000 plus 400 plus 50 plus 6. If I had, let's say, 1 there. So it would be something like, can you see that? So 10 to the power of 0, 10 to the power of 1, 10 to the power of 2, 10 to the power of 3. Okay, the 10 to the power of is the base, the 10 is the base. You could do the same thing at 2 to the power of 0, 2 to the power of 1. That's what we do in binary bases, right? It's invariant to the bases. The thinking is invariant. The place value system is basically whatever you're summing up stuff in their respective bases with the powers of that base, right? 10 to the power of 0, 10 to the power of 1, 10 to the power of 2, 10 to the power of 3. You could have the same number represented in bits, and then you could have said 2 to the power of 0, 2 to the power of 1, 2 to the power of 2. That's what a binary representation is, isn't it? When you talk about a binary representation. Now, when you are multiplying two integers, so 123 is multiplied by, let's go back to that example. So if I'm multiplying 123 with this, what you're essentially doing in long division is you're multiplying 123 by 400, but you're essentially doing, because there are 2 zeros, you only have to multiply by 4. There's 1 0, 123 by 5, and then 123 by 6. And the fact that you're shifting these things is equivalent to saying multiply by 10 to the power of 0, or 10 to the power of 1, or 10 to the power of 2. If you actually see how you have done long multiplication, 123 by 6 would be 738. Then 123 by 5 is actually 615, but you shifted by 1 because you multiplied by 10. And then 123 by 4 is basically 492. You shifted by 2 places. That's 100, 100th place. And you could have done that in shift by a bit if it's in a different base. So do you get an idea of what a long, long multiplication is, right? That algorithm is in d squared. Sorry, I meant d squared. It's a quadratic time algorithm. Every digit, okay? So we're assuming that they're of the same size, okay? Let's say that one was bigger. I could have made them same size by adding zeros at the front, right? Doesn't matter what I start with, I can come up with a representation which is basically a width of the longest of the 2 integers, right? And pad zeros on the other side, it would not change the result. So if I add 0456 to this, it doesn't change the result, does it? Okay. So d squared. And what is surprising is for millennia, that's the best algorithm we knew. Okay? The best algorithm we knew was of that kind. What we did in school. And then an honors student in a class, Anatoly Karatsuba, I think Kolmogorov, I might recall. Yeah, he was Kolmogorov's student, yes. So not very older than you are. Yeah? And he was listening to this really a big name in mathematics, Kolmogorov, who said, we don't have a better algorithm than a d squared algorithm. He says, let's go back and check. And he came back the next day and showed this algorithm to his professor, and he realized that professor assumed that you can't do better, but here's a simple scheme that we're now going to learn that you could do not in d squared, but d log 3 to the base 2, which seems, what a waste of time for getting that speed up, but as d grows bigger and bigger and bigger, and it's a considerable difference. So we will cover Karatsuba's algorithm. It's a divide and conquer algorithm. So the algorithm is a divide and conquer algorithm. And then just to give you a context, there's a beautiful algorithm called FFT from signal processing, Scheinhage and Strassen. Corman et al. Has a beautiful chapter. In fact, I think the best treatment of Scheinhage-Strassen, FFT, okay, deeply, these days everyone talks about deep learning and all these interesting ideas. It has notions of convolution. So FFT and convolution are very closely related ideas, okay? So Scheinhage and Strassen gave an even faster algorithm that ran in d times log d times log log d. I'm giving you a history. We're not going to talk about that algorithm, but good keen students should learn this. It's one of the gems in computer science. So it's in the CLRS book, and I strongly recommend for those who have some understanding of complex analysis in mathematics to at least and computer science to basically go and figure out what the FFT algorithm is. FFT is an algorithm to do what's called a discrete Fourier transform. We will not worry about what that fancy words mean, but in 1971, people said you could do better than d to the power of log 3 to the base 2. I must say that it's in a bigger sense, this algorithm is faster in asymptotically as d grows. As n grows to infinity, d grows to infinity. N is a number, d is the size of the representative number. Now, so the key point is that if you were doing FFT implementation, it only beats Karatsuba beyond a certain point. And that point is so big that almost every implementation that you see of BigInt will have a base case. A base case will always be hardware implementation. On top of that would be a version of Karatsubas, in fact, a generalization of Karatsuba. It's called Tomb3. Let's not worry about the precise details. So there'll be a version of Karatsubas on top of it. And if it goes way beyond a certain size, only then FFTs get involved. Okay, you see, but algorithmically speaking, we are computer scientists, we have to be excited about algorithms that, and in the limit, can do better. We're not just hackers that only focus ourselves on a certain base case or certain limited set of cases. That is good and more, okay? That's computer science is about reasoning in the limits. Now, when they came, Schoenhage and Strassen said, we have this d log d times log log d. This log log d is because we are not clever enough to come up with something better. That's tongue in cheek. It's very hard to come up with something better. So we have this extra factor, but they conjectured that if somebody is smart enough, they could whittle away. You wouldn't need that log log d factor. You could do this algorithm multiplication of two integers in d log d. I'm giving you a history so that I can give some context of this discussion. I think histories are also important here, although we'll only talk about one aspect of it in this part of this lecture. Okay? Now, drum roll, an Australian mathematician, is it, I don't know if he's in University of Sydney or University of New South Wales, one of the universities, I think University of Sydney from memory. He recently, I mean, in fact, I developed this material in 2018, I was teaching this, and in the previous, at least for 2 semesters, I did not have the 4th bullet point. While we were teaching one of the versions of this thing, there was a major announcement that happened that conjecture was true. Now, I must say, I understand the top 3 bullet points. I have no clue what they do. If somebody are very good in number theory, it's a mathematical argument. There's a paper. I'm quite happy for you to, I'm quite serious. If somebody understands it, come to me and explain it to me and I'll see if I can grasp it, okay? So I don't know this algorithm beyond the fact that it's a news item. It's tougher for me to process because I'm not a trained number theorist, okay? And they proved that you could actually do it in d log d, and it's a big thing. So they're going to get a Gödel prize if they've not already got one, okay? It's one of the topmost prizes that you could get. And the fact that they're in the Australian university should be something of a joy for us as well. Celebrate. Okay, so here's a case. UNSW. Okay, so it's New South Wales. I was wrong then. So University of New South Wales, he cracks this problem. Can you see that it's n equals 3-digit number? So here what we call d, they're calling n. So the best algorithm was d squared. The next best algorithm is n to the power of log 3 to the base 2. Log 3 to the base 2 is nothing but 1.58, okay? And then he says that, well, I could actually do it in d log d. So previous slide had everything in d's. Here they have it in n's, okay? So just a change of notation, that's all. All right. With that, a hopefully entertaining introduction to why we care about multiplying 2 integers. Let's deal with, it's easy to process this. I'll at least give you the intuition and then we'll pick it up. So don't worry about the symbols. I'm going to explain the symbols to you in a bit. So I'd always like to see this from the point of view of base 10 rather than base 2, although the slide is always talking about base 2. In fact, you never implement this in base 2. You always implement it in the powers of base 2. You can implement it in any base you want. Okay? There's nothing about this logic that works for only base 2. It works in any base, really. In fact, the implementation should never be in 1-bit processing. It should be byte processing or 2 bytes or whatever the word size is. So because it's easy to process it in whatever the natural word of your architecture is, right? With that caveat, let's say that I have 1729 times, so that's U, times 5321, some numbers. So I want to do U times V in this algorithm. Now, how many digits do you have? Okay. Now, in fact, there's nothing, if I had just that number, I could have made it a 4-digit number by padding a 0. Okay? You can change it to any length you want by padding zeros. So what you have is a number that is here d equals, let's call the width equals 4 bits. I'll call w equals 4 bits. Now, if I break that number into halves, so 2-digit on the left, 2-digit on the right, I get numbers 17 and 29 on the first side, 53 and 21 on the next side. Now, if I multiplied it by 10 squared, added it, would I get that? If I multiplied this by 10 squared, added it, would I get? Yeah? See that? Do you understand what I did? So if you look, that 10 squared is, if you started with 17, if I multiplied by 10, it shifts by 1 position. If I multiplied by 10 squared, it will shift by 2 positions, right? That's what if I. So essentially, what I am trying to do that is in base 2. So here, W equals 2 times D, so D equals 2, right? The width of these things are 2. W is 2 times D. So if you started with some integer u, let's assume that you are representing in base 2, you can think of that to be some even number. If the minimal code is odd, you can add a 0 to the most significant bit to make it even, right? So you can actually make things even, and you have exact half of things that are before, half that are most significant, and a half that is least significant. You can do it with both numbers, and if you can, what I've done here is 2 to the power of d, which is the width of the half, times u1 plus u0 is u, just as d equals 2 here, okay, 2 to the, so 10, the base is 10 here rather than 2 because I'm doing everything in base 10 here, 10 to the power of what's d, d is 2 here, times u0, so essentially we're calling that u1 and u0, so we're going to say that's u1 times 10 to the 10 squared in base 10, but 2 to the whatever in base 2. Okay, base 10, base 2, there are essentially ways of representing numbers, right? They're equivalent. Are you convinced of that statement there, everyone? If you're convinced of that statement, then product of uv can be expressed as some algebra of product over halves of that number. So most significant half and least significant half. So u1, u and v is, u is this, v is this, u times v is nothing but this times this. I've not done anything beyond simple algebra here. Now if I expanded this term, take it for granted that if I multiplied this, you get u1 v1 times 2 to the power of d times 2 to the power of d, that's going to be 2 to the power of d plus d, that's 2d, and then so on. Okay, I'm just going to get some expansion like that. You can go and check if this is true. I'm just going to give you an idea of where we are headed. Now, if that's true, so this term is same as this term. the last term is same as last term. My claim is everything inside this bracket, so this parentheses is same as that parenthesis. What have I done here? I have added a product and subtracted a product. So these are introduced. U1, V1 has been introduced and also subtracted. So they cancel out. They don't have to worry about it. Similarly, U0, V0 on the other side, they've been subtracted and added. They cancel out. So what's remaining is essentially U0, V1 and V1, V0, and that's nothing but what you have above. Why did I do this? It's because it allows me to factorize it a bit more cleverly. Or at least Karatsuba factorized this is same as this line is same as this. And what I have done here, it's very, very easy to see this statement is equal to this. So this term is equal to this term is equal to this term. And then what he has done is Karatsuba took U1, V1, that's right there, U0, V0, right there. But everything, all those 4 terms in the middle have been factorized in this form. Okay, we'll see why that factorization is necessary in our thinking, but let's just follow along. It's just simple algebraic manipulation. There's nothing great more than high school stuff out here, except doing it in a special way. And then if I then distribute, so I got this term into this form. If I distribute this 2D goes with U1, V1, it goes with these terms in the middle, and it goes with these terms U0, V0. So, but you already have a U1, V1 there with 2 to the power of 2D, plus now you have a 2 to the power of D. So if I factor out U1, V1, I get that term. Similarly, at the end, 2D is a factor of U0, V0 plus U0, V0 outside it. So it's going to be, if I factor out U0, V0, you get 2 to the power of D plus 1, and then everything in middle is that. So if you actually go and see, I've already, all I've done is just distributed stuff. Now this is important. I'm going to go to the next slide. So whatever you saw in the last line was this. Now look at that formula at the top. What's that formula? The formula is saying that I have started with a 2D of some width number. U and V are 2 times D bits long. And I've expressed that as a product, so the multiplication of a 2D bit numbers, 2 times D bit numbers, have been expressed as some algebra over product of 3 D bit numbers. So U0, U1, V0, V1 are all D bits long, half the size. Originally you have 2D, now you have half of it, but instead of 1 multiplication, you have 3 multiplications. Okay? But all these multiplications involve half the size you started with. Now that is, so you're taking a 2D bit multiplication, forking it, branching it off into 3 D bit multiplications. So that's the divide and conquer part. Now each D bit can be branched off into 3 D over 2 bit multiplications. Okay? So you can, I'll draw this if that's not intuitive enough. So I'll just say this and we'll end the discussion for the day. So you have a 2D bit multiplication. You kind of branch it into 3 D bit multiplications. This gets branched into D over 2 bit multiplications, and so on. And each of them, D over 4, D over 4, D over 4, and so on. Yeah? Okay? Can you see that? Can you see the divide and conquer part of this? Where you're taking a 2D bit multiplication and then transforming into a 3D bit multiplication. The idea would be that any other addition and multiplication by 2 to the power of 2D is a linear time operation. Why? If I have to multiply by 10, I just shifted by 1 position, right? Multiplied by 2, shifted by 2 positions. Shifting, multiplied in whatever base, is like shifting the bits or the digits, the radixes, right? So essentially Everything else is simple left shifting, as it's called, showing there. So in whatever base you're doing. And then some addition and subtractions, both of them are linear time operations. So the claim is that the time taken to do a 2D-bit multiplication is 3 times time taken to do a D-bit multiplications plus some constant times D. The shifting and the summation is constant. Now, if you solve that recurrence, you are going to get a D to the power of log 3 to the base 2 algorithm. So that's basically the Karatsuba's method. Okay, I'll stop here. I think there's an example, self-study, just take an example in binary basis and follow through this example of what this division is. So you would want to, you can actually do it on base 10 and see if you can prove it to yourself. You need a calculator, a computer in front of you, and base 10, and it should work. Okay, I'm going to stop here. I hope you have some semblance of quiet during the break. I know usually for you, break means catching up on other assignments, I suppose. I can assure you we're all in that state with a different problem. But from my side, you'll get a sufficient time for assignment 2. 4 weeks is pretty generous, I would say, for an assignment. I'll release it sometime in the middle of this week. I have to run it past my teaching team to figure out if everything is on track. And then I will have consultations. Please do come to the consultations. I really encourage you. So it does take a lot of effort to find holes in my calendar, and I really blocked out Tuesday, Wednesday, and Friday, 9 to 10. 3 of them. If you're busy on one, I hope one of the 3 would be available. Now,